1. Failure model. A failure model describes the conditions under which a material is considered to have failed. It specifies the point at which the material can no longer withstand applied loads, and failure is identified. Failure models are often based on specific criteria, including yield criteria, fracture criteria, fatigue criteria, and creep criteria. Examples of failure models include von Mises yield criterion for ductile materials, maximum principal stress criterion, maximum principal strain criterion, etc. 2. Damage model. A damage model focuses on predicting the evolution and accumulation of damage within a material under deformation or loading. It provides information about the degradation of material properties due to damage, which can lead to eventual failure. Damage models involve concepts such as damage initiation, damage growth, interaction of multiple damage mechanisms, and material softening. Commonly used damage models include linear damage accumulation models, damage mechanics models, and cohesive zone models for crack initiation and propagation. In summary, a failure model defines the criteria for considering a material as failed based on stress or strain conditions. A damage model predicts the evolution and accumulation of damage within the material, offering insights into material degradation before ultimate failure. Thinning. Thinning is a failure mode that is often associated with materials or structures undergoing plastic deformation. It specifically refers to a reduction in thickness or cross-sectional dimensions of a material or structure as a result of plastic deformation or other deformation mechanisms. Thinning can occur in metal structures subjected to plastic deformation processes, such as forming or stamping. In such cases, the material experiences localized plastic flow, resulting in a reduction in thickness in certain regions. Major in-plane stress failure. Major in-plane stress failure refers to the failure of a material or structure under the influence of significant in-plane stresses. In-plane stresses are stresses that act within the plane of the material or structure, typically in the XY plane. These stresses can result from various loading conditions, such as tension, compression, or shear. Failure under major in-plane stress may manifest as yielding, rupture, or other forms of structural failure, depending on the material properties and the nature of the applied stresses. It's worth noting that the specific failure mechanisms and modes depend on the material properties, loading conditions, and the structural configuration. Thinning is often associated with plastic deformation, while major in-plane stress failure can manifest in various ways, including yielding, fracture, or structural instability, depending on the material's behavior under stress. In engineering simulations and analyses, understanding these failure modes is crucial for predicting and preventing structural failures in various applications, such as metal forming processes, design of components under load, and the overall integrity of structures. Let's adapt the information for LS-Dyna simulation. 1. Failure model in LS-Dyna. In LS-Dyna simulation, a failure model defines the conditions at which a material is considered to have failed. It specifies the point at which the material can no longer withstand applied loads. LS-Dyna provides various failure criteria, including yield criteria, fracture criteria, fatigue criteria, and creep criteria. Examples of failure models in LS-Dyna include the MAT_024, Johnson-Cook, Material Model for Metals, MAT_058, Composite Failure, for Composites, and others. 2. Damage model in LS-Dyna. In LS-Dyna, a damage model focuses on predicting the evolution and accumulation of damage within a material during deformation or loading. It provides information about the degradation of material properties due to damage, leading to eventual failure. LS-Dyna incorporates damage initiation, damage growth, and interaction of multiple damage mechanisms. Commonly used damage models include MAT_072, Modified Johnson-Cook damage, for metals, and MAT_58, Composite damage, for composite materials. In summary, in LS-Dyna simulation, a failure model determines when a material is considered failed based on specific criteria, while a damage model predicts damage evolution within the material. LS-Dyna offers various material models and options for accurate simulation of failure and damage behavior.